guess it's kind of topical again, isn't it? NASA just had their whatever their mission was to crash a satellite into a meteorite to see if a small change in momentum a long way out can make it deviate by a small degree. So this was, I think it's 2012. Anyone here seen a meteorite ever? I remember we used to give hardshell kayaking lessons at Sunnyside in Belfont, where the Penn State have a slalom course. And I remember seeing one of these streaking across the sky probably 15 or 20 years ago plus. This is in Russia, where it was caught on everyone's dash cam. So when you watch crazy drivers with the dash cams on YouTube to fill out your evening, these are the same dash cams, I guess, that are picking up some of this stuff. So relevant only because we're talking about conservation of momentum today. So I'm not going to show them. What else? Let's get something a bit more closer to our interests. I'll turn the volume off so you can see what these are. A Pelton wheel. So this is a way of generating rotational motion from straight line motion, just like a steam engine. And so it's just a jet of air on these cups rotating on a so-called Pelton wheel. And that would be used typically to grab whatever the fluid is. It would typically be water rather than air because water has more mass, and momentum is mass times velocity. So the higher the momentum you get, the more energy you get transferred in your system. And so those are the kinds of things that we'll try and talk about from now onwards. You've seen this before as well. I guess we're still 10 minutes out, and so the jet lev, we did a quick example with this with Bernoulli to be able to calculate exactly what flow rates we needed to be able to lift someone off the ground, 100 kilogram weight, a person off the ground, and sustain them. A quick and ready calculation which we could do with Bernoulli. Of course, Bernoulli is conservation of momentum, embodies that. F equals ma. Ma is rate of change of m times dv dt, which is rate of change of momentum. And so these are the ones that we've seen before. If you have a cool 15K or so to spend, this is a proverbial test question. Everyone looks up. I had to play your buttons. But yeah, we've alluded to this before. If you've looked through any of the questions for the second test, which would, I guess, finishes at the end of this week, is the material for the second one. And it's the sleeping giant, so to speak. Mythbusters. They never come back at us and ding us for copyright infringement over YouTube, which some people do. I guess I haven't got this set up yet. And so you can, I don't have the closed captions on. I guess I could do. Unavailable, okay. Well, you can guess what they're doing. They're taking a gas canister. They may have something like 70 megapascals inside when you buy these things. Have to have high pressures to get an appreciable mass of gas in them. And so when you move them, you also screw this cap onto them around the neck. And when you have them in a lab, you always have them attached to a leg of a table or some proper upright. And the reason for it is this little game here where they take one that's lying down, they guillotine off the cap, and so it's activated, and it goes through one block wall, tries to go through a second block wall, I think, when it gets to the other side. And I guess you don't want that coming out the side of the building on the 5th floor and launching itself into the air. And so yeah, it's quite a powerful thing to see. The slow-cooled sleeping giant. What else have we got? Again, conservation of momentum. You've probably done this little game with propane, a blowtorch, and a Coke bottle. You've seen the other Mentos tricks as well, right? You put Mentos in Pepsi or Coke, and it does the opposite. And what else have you got? Yeah, and something perhaps more like what we're dealing with. And we'll deal with this today as well. And so a so-called Undershot Weir. Undershot meaning that the water goes underneath it as opposed to over the top, overshoot. I guess it's usually used in terms of water wheels. You know, when you have a water wheel and it's supplied with water on the top and the weight drags it down, or you can also supply it underneath and just push it. So undershot and overshot supplies of water wheels to create energy. And so this doesn't use to create energy, but we talked about this last time we met, I guess, at the end of week 5. We talked about measurement devices. Don't know what this is. Pinned down by Hurricane Agatha. I guess I don't want that. Who knows what this is? But I can go back to... it won't go back now, so anyway. Is there a way to get it back from where it was? I guess you can do history.
There's an arrow at the top.
Yeah. Can you do it other than just going history? I'm not sure. If you catch it early enough, well, the replay button's on, I guess it is. And so we talked about this before in terms of measurements of flow rates, right? You take the upstream elevation, the downstream elevation, they're different. We can use that as kind of a change in pressure between upstream and downstream and use that to calculate what the volumetric flow rate is or the mass flow rate in the system, and is a convenient way of being able to measure a flow rate from just looking at the two elevations, upstream and downstream. So that's that. I can't remember what the last one is. Oh, I guess, yeah, nothing. I thought this is an interesting article talking about the energetics of kills. So, of course, energetics is you have to expend energy to kill something, but you get some calorific value from what you eat. So I guess not so relevant to this. So that's kind of where we are with this. So welcome back. After your activities, you've seen the relative scores from last year for the test. I think they were good this year compared. So I'm kind of happy that people heeded the message from that I've been trying to make for many, many years now, but perhaps has fallen on fertile ears in terms of how things worked out. I think that's done, kind of a necessary part of what we do, just to bring us up to speed and see how we're all doing. And that's done. Hopefully it worked out well for you. If not, then I guess the next ones are in a few weeks. We won't think about that now. We'll just think about what we are moving on to in the next little while. The material from online material from last week, I guess, will be open for the Monday one until this Monday as a courtesy, since you had a busy week last week and might not have got round to looking at the extra credit materials. And then I guess Wednesdays will probably close on Monday as well. And then Fridays will close on Wednesday. So the same system, but with a bit of leeway for that. And also the assignments, I guess, which were due probably last night. So that's done. So that's kind of where we are. If you looked at the materials online already, I mean, I don't know whether it's worthwhile doing this or not. Perhaps of course, you can't do this quite on YouTube. You can do this on the recorded videos. And so you can run it at 60 speed, so a 60-minute class takes a minute to run through. And so last week, the first class was talking about control volumes, conservation of mass, and the fact that we have to be able to look at a variety of coordinate frames. The example that we go through in the class was going down a well bore, looking at the substantial derivative in temperature to be able to record temperature as you go down by running a sonde down the hole. And this uppercase dt that you see here is being able to define in the reference frame of the sonde going down the hole in terms of not only a time derivative, change in temperature with time, but also a change in temperature with space, dt dz. And so we need to be able to accommodate different reference frames. The second one was to deal, we've seen this before, again 60 speed. 30 speed will take us 2 minutes. Never quite sure whether this is real or a spoof. But using this example of a filling container to be able to do the analysis. And all we do is that we use mass in equals mass out, and the difference between those is some kind of accumulation. We can define that in terms of Reynolds transport theorem, which is just a convenient way of being able to write behavior between upstream and downstream along a stream tube, but write it much more generally. And we define some rules, which we'll again look at maybe today before we get started, just to be able to define the differences. And then we went through an example of filling up a beaker to show you that we can look at a static control volume in which fluid is coming in, a moving control volume which moves with some of the surfaces, or a deforming and moving control volume which allows the top surface to move up as the water rises within the beaker. And we just made the case that for all of those systems, since they're the same systems that we're looking at, and I think this is the same deal here, then the answers that we get for how long does it take to fill this beaker is the same, irrespective of which of those systems we use. So it's just a convenient way to be able to do that. So if you haven't looked at these, this is kind of a precursor to what we'll talk about today, merely making the case that if we look at a moving fire ship, then if you're standing on the ship pointing the hose at 1 meter a second and the ship is moving in front of you at 1 meter a second, then to a static person on the dock, the vector of sum of those two, 1 meter plus the ship moving at 1 meter per second, appears that it's moving at 2 meters per second. And so we need to be able to move between those systems to be able to do that. And so this is the point in making the fact that we have to be able to choose those different moving coordinate systems. So it's a bit esoteric in some respects. You probably, you have a bucket, you fill the bucket up, it takes a certain amount to fill the bucket up, the bucket has a volume, you can calculate the volumetric flow rate from dividing the volume divided by the time it takes to fill. That's really what we're kind of doing in all of these. It's just that it's got a little bit of an extra flavor to it in dealing with it. So I encourage you to look at those before the extra credit, I guess, disappears. And so I won't look at the recording from last year, but I'll go to the recording of what we'll talk about this time. And so I'll do, as we've done before, kind of a brief summary of some of the things that we're talking about. And that is that we're dealing with Reynolds transport. So to bring us up to speed from last week, we talked about conservation of mass. And in Reynolds transport theorem, we have this extensive property and an intensive property, and they're just linked that uppercase B is mass, and lowercase b is uppercase B divided by mass, which is equal to, since B is mass, this is equal to 1. And so if we put these terms in here, this is mass. We're only going to look at steady state systems, where this is equal to 0, where this b is equal to 1, and this b also is equal to 1. Then this term in our shorthand that we talked about last week will look something like this. I guess you could think of this as kind of a stream tube, right, with the top and bottom confined. If we define a volume or velocity 1 into the system and a velocity 2 out of the system, and we define a volume of this control volume, then this equation, if we write it out in the shorthand which we developed last week, so I'm just recapping this, is going to be this term is just going to be density times the rate of change of volume plus rate of change of density times the volume plus the sum of the density times the area times the velocity equals 0. So this is conservation of mass. You know, before what we've done for if I just do it in a more familiar way of saying it, this is a streamline, right? We've said this before. This is V1. We have a pressure here. We have an elevation here. And we have a velocity here. And we have a pressure and an elevation. This we wrote as rho V1 A1 equals rho V2 A2. This A is, of course, the cross-section area, right? This was our conservation of mass as we did before. And so our requirement for Bernoulli, if you remember, there are 4 requirements: inviscid, no viscosity, no eddies, no compressibility of the fluid, but the most important one was steady state. And so steady state means that there's no net accumulation of volume in this stream tube. So now with Reynolds transport theorem, we've gone a step beyond that. We've said that you do have accumulation. So accumulation here, and this term here would, if we wrote it out in full, be something like, this would be rho A1 V1 plus rho A2 V2. That's what this term is here. In other words, this. And these other 2 terms are the accumulation terms. And they're pretty straightforward. So this is a density with a changing volume. So you could think of this as being a bucket that you're filling up with fluid. And initially the level of the bucket is here, and maybe that level rises up to be something else. So in other words, the density stays constant, water, but the volume of this control volume changes to accommodate it. And this would be a cross-section of a tire. So the volume of the tire stays constant, but the density of the air that's going into this tire changes. It gets higher density as the pressure changes, the essence of pumping up a tire. So these are 2 terms that we now allow through Reynolds transport theorem. So Reynolds transport theorem is this rather nasty looking expression here. For the case of conservation of mass, we just have to remember these 2 terms, and substituting into this first term gives these 2 terms. See, it's a rate of change of a control volume times the density and its volume. And so the density and the volume and a rate of change is either the rate, just by splitting it up by the product rule, is either a rate of change of volume and a constant density, or a rate of change of density and a constant volume. That's all it is. So that's kind of what we have here. And so the other things that we talked about last week, you'll see, is this is the example that you perhaps saw fleetingly. This is my favorite shape for a ship. And I made the case before now that if the fire ship is shooting out water at velocity w, and the ship is moving at the velocity of the control surface, then to a static observer, this ends up being W plus VCS, which is equal to V static. That's all this equation is. So it says that if you're standing on the quayside, you see the fireboat going past you at 1 meter a second. It's squirting out forwards at 1 meter a second. Then relative to you, this jet of water is moving at 2 meters a second, right? 1 plus 1. If they're going in opposite directions, it's the vector sum. So you subtract one from the other. Okay? So that's kind of a recap of what we were doing last week when you're otherwise engaged. And so what we'll do today is, instead of looking at mass, we'll look at conservation of momentum. And for conservation of momentum, our extensive property is mass times velocity. Our intensive property is the magnitude of that per unit mass, which is equal to mass times velocity over mass, which is equal to just velocity. So be careful that I always try and write a bar through my volumes to distinguish them from velocities. And so what we could do, if we go back to here, so I'm going to scribble these out. And write them back in, what I scribbled. This is mass, so this is volume. So now, if I put these blues back in here, this term here is going to be mv. This term here is going to be v. And this term here is also going to be v. So these are v's. These are vectors, so they have 3 components. Let's not worry about that now. But let's think about exactly what this term is. This term is d mv dt. And of course, you've seen this before, because this is equal to sum of forces. This is Newton's second law. The rate of change of mass times velocity is, we could also write as being mass times the rate of change of velocity, dt, and this is just acceleration. Right? So this is acceleration. So this first term is the sum of forces. So we can replace this first term with the sum of forces. If we now look at the rest of it, then we have 2 other components. We're going to talk about this one. This is rate of change of momentum, accumulation. So if you look at this expression, density times a velocity multiplied by a control volume. So density times a volume is a mass times velocity. So this is momentum. And so this is how much momentum changes per unit time in our control volume. And to make our lives easy, we're going to assume that this term is always 0, just so we're dealing with steady state. And so we're going to assume this is 0. And the only term we're going to worry about is this, which will be density times velocity, times velocity times area. Remember that the dot product is just whether the stuff is in or out. Let's not worry about the dot product. And so I suppose I could have written that more usefully as the sum of forces is equal to the velocity times density, velocity, area. Sum of. And
Is V supposed to be a volume?
no, these are both velocities. If you go back up here, we've got rid of this. We don't care about this volume here. There's no volume in here. It's just an area. Okay. Thanks for asking. You're usually right, but not this time. Sorry. And so this is going to be our control volume that we'll work with. If we wanted to, we could also draw on this, although we're not going to use it, our unit normal. So in other words, if you remember, or if you've looked at the stuff already, this dot product of velocity times the normal to the boundary just means that if the velocity is aligned with this normal, this is positive. If it's aligned in the opposite direction, then it's negative. So we know that. And so it's useful for us to write things this way because, of course, you realize that this whole term here, I should draw these curly brackets underneath, which would be helpful. This is mass flow rate. So density times a velocity times an area is just a mass flow rate that goes across a boundary multiplied by another velocity. And so when we can write these things as in shorthand, then if we wanted to, then, and we'll do some examples today, then this is our conservation of momentum law. We have to realize that, of course, these forces and velocities are our right-hand rule forces and velocities. There's three of them, x, y, and z. And so that this whole equation is really written as forces in the x direction are equal to, or sum of forces in the x direction are equal to the velocity in the x direction multiplied by the mass flow rate. Sum of forces in the y direction are equal, these are summations, of course. So this is our rule that we have to take care of and that we use. And so this term, these terms together, we'll typically use them individually, but you could write this as a matrix equation. We don't need to, we'll deal with them individually. So this is conservation of momentum. And this is the equivalent of Bernoulli. So in other words, weak number 4. But it's a bit better than Bernoulli because it allows us to calculate, throw some forces into this system as well. And so this is the control volume we'll look at. I've drawn it just as a square control volume, but we can look at it. This would be velocity 2 and velocity 1, and we can do some examples. And I'm going to write also down here the other expression that we have, which is, and this is conservation of mass. And so it's useful to put them together here, because conservation of mass is what we've said for streamline that we drew here, right? That we could just draw as this equation here. And so that's exactly what this is, but it has now accumulation terms in it. That's the only difference. And we can do it for any kind of shaped control volume we want to. It doesn't have to be a streamline. And Bernoulli, which this would have been week 4, I guess this would have been, it was week number 5 really, which is kind of backwards, and week number 6 last week as well. This is mass flow rate, and that's just what these are. And so the useful thing is this: if we're looking at summing up the mass flow rates, and if we do this on this particular system, the mass flow rates would be V1 A1 rho plus V2 A2 rho equals 0 for this particular case here. But we realize that we have to take care of this dot product. And so we'd have talked last week about the fact that if the velocity is going into the control volume, it's going the opposite way from the unit normal. So this would be a negative that gets put on this velocity. And because this velocity is going in the direction of this, you know, if you come back up here, there's a dot product that we've just dispensed with. We've thrown it away just by noting that if the dot product is the normal is the same direction as the velocity, that's positive. So mass flow rates out of the volume are positive, and mass flow rates into the volume are negative. That's all we have to remember. And so this would be a positive here. And so if I kind of move this thing over, so this negative and this positive have to be baked into this. So now we have to think about what that means for the sign convention here. And the sign convention for momentum is that this would be a positive force in the x direction because it's acting in the positive x direction. And so it could be this force, or we could define a force going the opposite. That would just have to be accounted for as negative. But these velocities, so these mass flow rates take the same sign convention as the green. And so these mass flow rates would take the same sign convention as the green. So mass flow rates in would be negative, mass flow rates out would be positive. But the velocity is a Cartesian velocity. So this velocity 1 is in the positive x direction, so it's positive. This velocity v2 is also in the positive direction, and so we account for that as positive. So these are positive. Positive vx, positive vy, and positive vz. So that's the sign convention. So this is for conservation of mass, this green one here. Mass that's used in the conservation of momentum equation as well. And this one would be for momentum. That's it. So that's about as plainly as I can explain it. And so the proof of the pudding comes in how we would use this. And so really, again, cement in your ideas. Conservation of momentum is just Bernoulli. We could write it as Bernoulli if we wanted to. It'll turn out to be that way. You remember when we wrote it as Bernoulli, it came out as something like z plus p over gamma plus v squared over 2g equals constant. And that's exactly what these equations are. These are the forces due to pressure and elevation. This is the kinetic part. kinetic energy, if you like, conservation of momentum, these terms here. Don't worry about the fact that there should be an equal signs here or whatever, just do it based on sign convention. But that's essentially what we have. So this is basically Bernoulli equation. The only useful thing about writing it using Reynolds transport theory is that now we have baked into this some forces which we could use to calculate forces acting on structures. And so the most simple structure we can use is the example we looked at the beginning of class. If I can bring it up again, actually it's still on here, is this. So maybe what we'd be interested in doing is saying, let's not figure out how quickly the fluid is flowing here, but let's figure out how big and strong we need to build this weir so it doesn't break when it flows between upstream and downstream. And so now the question is, how do we calculate the forces acting on this weir to be able to design it appropriately to be able to resist those? And so that's the quick example that we'll do. We'll just do an example to do that. It's the same as is in the book, I guess. I love my new computer. It's not stalling on me so far. I guess fine. So Reynolds transport theorem, yeah, we didn't do all this. So this is the idea of the example. And so I won't do it from here. I'll do it from kind of first principles, just walk through it. But here's the idea. You have a weir. We could put this undershoot gate all the way down, and we could look at defining the behavior of this weir, or we could look at pulling it up, and then I guess the question would be, are the forces that are on this weir bigger or less than it would be if it was fully down? And how much bigger or smaller are there than this? And so it's easy to be able to do that example. And all it means is that we have to do a couple of things. Because we've got forces in our system, what we could do is we could make a nice free body. And so the free body that we could choose would be something that would go around the system like this. You've used a different color, you'll see it. And then look at the forces acting on this box, just as we'd drawn before. And now this box also includes a reaction that we'd have on this gate, which would be acting in the minus x direction, which we could calculate. That would be the force we'd want to be able to figure out what's going on. And so the free body that we do would be related to this. So let's do an example that has that, and I'll go through it. Now you can correct me when I get wrong on this. Now's your chance. Deal? So this is my attempt to draw it. This is my control volume. And what do we have? We have a velocity v1. We have a velocity v2. We have a force. Well, okay, let's do this the simple way first. Let's do it so that we, first of all, draw the gate all the way down. I'll add that. And so if that's the case, then velocity v2 is equal to 0. We have a reaction R1. We have, I'll use green. We have a pressure distribution acting on the back. And we don't care about the pressure distribution acting here. We know that this pressure distribution creates a pressure P1. And we know that P1 is equal to the height of the centroid times unit weight times the area. I'm not going to draw a very good perspective drawing, but take this, the fact that this width here is equal to B. And this height here, which I didn't define, I think in the example in the book as well, is uppercase H, and this is lowercase h. So height of the centroid this is going to be, let's do it in green just for consistency. Height of the depth of the centroid is equal to h over 2. The unit weight and the area is equal to h times b, which is equal to a half h squared b times unit weight. In this case, if V2 is equal to, so this is closed, I guess. Then if that's the case, V2 equals 0. If V2 equals 0, then V1 equals 0. No flow, right? And so we don't have to worry about these either. And so this has to equal R1. So this is just a static case. Not very different from question on Wednesday on your test, right? Similar. So by definition, the force acting on the gate is equal just to the pressure distribution. These velocities don't matter at all. So now the next step is the gate open. So now V2 is not equal to 0, and therefore V1 A1 is equal to V2 A2. We could constrain it if we wanted to. So this is our conservation of mass, right? And so let's go through this expression now. So we're going to sum forces horizontally, and we're going to make them equal to the product of velocities and mass flow rates. So let's look at writing this out. So forces in the x direction plus velocities in the x direction, mass flow rates has to equal 0. So what are our sum of forces? Well, we have one extra force now to take care of. And you can think of this as being applied on this gate here. So I'm taking the gate out. Gate is gone, so velocity is now finite. And so the sum of forces would be, this would be P2 as a force. So this would be P1 minus P2 minus R1. So this, and this, plus velocity 1 times area 1 times V1 for this velocity here, right, which is constant. I guess if I wanted to, I could draw the velocity as being like this. I don't really want to because it kind of gets confused with the pressure distribution. But the velocity is constant right the way across this section. Likewise, velocity V2 is constant across this section. So I'm just going to do this as blue. Sorry for the mess. And then this is going to be V2 A2 V2 equals 0. So now I'm going to come back to here and deal with our sign convention. Remember the sign convention. Sign convention is for mass flow rates. It's positive if it's coming out of the mass, but negative if it's going in. And for the momentum part, this is a Cartesian velocity. So positive if it's in the x direction, negative if it's in the negative x direction. And so this is going to be, area is just h, uppercase h times b. This is going to be lowercase h times b. The conservation of mass, this is into the volume, and so it's negative. So there would be a negative sign. I'll do it outside. So there's a negative sign here. This velocity is out of the mass, so this is a positive sign here. So this is for the conservation of mass part. And V1 is in the positive x direction. So I'll change my color. So this is positive. V2 also is in the positive x direction. So this. We know what these forces are. If I go back to green, what are those forces? They're going to be the same as this. This is going to be a half. I want to be green. It's not easy being green. Half h squared b times unit weight minus a half lowercase h squared times b. Depth of the centroid here is halfway down as well, times unit weight minus r1. And then if I do the correct summations of these, so a positive and a negative is a negative, a net negative. So scalar value of V1 H B V1. Positive positive is going to be a positive. This is going to be V2 lowercase h b V2 equals 0. We have more things that we need to know here. Remember, we could take this, and if we wanted to, we could use conservation of mass, because we can relate this here. I'm not going to do it, but we could relate V1 A1 is equal to V2 A2. And so we could get rid of one of the velocities. And so if we knew, typically the easiest thing to do is to assume that because this is it's like the big volume assumption, V1 is going to be small compared to V2. So V1 will be small. So V1 squared will be small as well. And so this term may disappear because it's small. But it allows us, if we manipulate this, to be able to say that, so I guess we could say that R1, by subtracting this onto the other side, is equal to half h squared b unit weight minus a half lowercase h squared b unit weight minus v squared hb plus v squared hb. And so if you remember, before when the gate was closed, this was our expression. So we're getting to the punchline. Don't get anxious. So this was the full static weight acting behind our gate. So now we have the full static weight behind our gate is equal to R1, but we lose a piece. H is always bigger than 0, B is always bigger than 0, unit weight is always bigger than 0. So this is a reduction in the weight because it's above and we've got water flowing underneath it. V squared is always going to be positive, so this is an extra component that reduces it. And we can also relate this to, I didn't put the right numbers on this. This is V1 and this is V2 on these. And so we have the same reaction, but it's reduced because we've pulled the gate up. We don't have so much force acting on it now because we don't have this. We have this acting in the opposite direction in the same way as R1. And so it's reduced by that amount. And also we have this dynamic component. And so if you look at the solution in the book, it's essentially the same as this. And that is that the reaction acting against it is what we had before when the gate was down, which is this amount here. But it's reduced by an amount because, one, the gate is up and the force isn't acting against it. Maybe you can make the case that there's some shear stress acting on the bottom, which of course reduces the force that's on the gate because this is acting in the same direction as the reaction. So if there's a shear force acting on the bottom, this also reduces the force. This is the downstream velocity V2. They've called it U2 in the example, which is this. And in the example, they neglected the amount which is flowing into the upstream part, which is negligible. And this acts as a positive. Was it a positive for us or was it a negative? Yeah, it's a positive for us. So there's a small amount added for this positive amount here. That's it. And so all we've done is we've used Bernoulli essentially, which is embodied in this expression here. This is essentially, we can think of as Bernoulli, just written in a different way. And it's better than Bernoulli because it allows us to include some random forces in our system. And in this case, the random force was the gate that was acting. So nothing more than that. And so that's the theme. And so we can use that. So we just need to be mindful. So I guess the lessons from today are that we can look at the fluxes of mass into our system, and we can look at the fluxes of momentum into our system. We have to do an appropriate accounting for them, given the fact that a mass flux into our system is negative, a mass flux out of our system is positive if they're aligned in the perpendicular to the surfaces, and the momentum flux is always positive in the Cartesian direction because Newton's second law, F equals ma, is always written relative to the reference frame of our world, not just a local reference frame. So X, Y, and Z. I guess there's another quick example that maybe we can do here. Same idea, perhaps a bit more interesting. I can't go through the full example, but I can show you the individual components to it. If I use the same colors as before, then what would those be? The blue would be for velocities. So the velocity into the system is this. Velocity out of the system would be this. The control volume that we might put around this is to draw a control volume here. You see it's just a dashed line that's been drawn on the figure, but I've drawn it as a box. The control volume has a force that's applied inside here. And I guess there would also be pressures that are applied into the control volume. P1 so green is for pressures. Sorry, this is P1 and this is P2. So this is the pressure distribution. So the force acting P2 would be equal to the pressure times the area The velocity would be v2. And so the two terms that we need, I guess, would be the sum of forces in the x direction plus velocities times area times velocity equals 0. Summation on this. And so what are the forces? If we were to write those out, it would be P1 uppercase plus P2 uppercase minus Fx plus V1 A1 V1 plus V2 A2 V2 equals 0. So this is the sum of the forces. The sum of the forces are the acting at this magnitude here. So uppercase P1 is equal to the pressure times the area, which is this. P2 is going to be the pressure times the area here. Of course, P2 is going to be atmospheric because it's coming out as a jet. This is the pressure that the pump is pumping at, not necessarily 0, almost certainly not 0, right, if it's being the pressure in the hose. So we have each of these. We'd like to know what this force is. And we have a velocity times an area times a velocity, and we just have to do the appropriate accounting for this. So the appropriate accounting would be, this is, for the first product, this is the mass flow rate, area times velocity. It's into the control volume, so this would be a negative. This velocity is in the Cartesian coordinate direction, so this is a positive. So all I'm doing is going up by that box. V2 is coming out of the control volume, so this product here is a mass flow rate. It's a positive because it's coming out instead of a negative. And it's in the negative Cartesian direction, x towards the right, and so this would be a negative. And so you just have to do the summation. So you could do things rigorously with a dot product, or you can remember physically what the dot product means. And what the dot product means is merely to follow this sign convention, which is given here. And that is that the dot product for the mass flow rates, if it's out of the volume, then it's positive. This is backwards from the other diagram we drew. If it's into the control volume, then it's negative. And, well, I think it's easier to go back to my diagram because I haven't introduced that. This diagram here. If it's conservation of mass, if it's into the control volume, it's negative. If it's out of the control volume, it's positive. And for the Cartesian magnitude of this velocity here, it's always in the Cartesian direction. So this is in positive x, this is in positive x, and of course the value of the force would also be a positive force. So that's it. So we're right on the money. Okay? So you just have to take care of the sign convention. So we'll do a bit more with this. We'll talk about applying this to moving control volumes. So obviously this is a relatively simple case because this is a static control volume. It's definitely steady state, right? Because if we take a snapshot of this now and a snapshot of it 10 minutes later, the flow velocities in and out are identical. They're not changing. There is no net accumulation in this volume. The same amount of flow that comes in ultimately leaves because we've prescribed that. And so that vindicates our choice of throwing this term away here which represents the net accumulation of momentum in the system, which we don't worry about. So all the cases we'll deal with will be kind of steady state. I say kind of because one of the examples we'll do is the sleeping giant, you know, the gas cylinder slipping across the floor. And of course, that's only kind of nominally steady state, because if you look at the pressures inside the gas cylinder at time zero, they're relatively high. But if you look at it 10 minutes later, when it's depleted its pressure, they're low. And so it clearly isn't steady state because the pressures don't stay. But we can get away with dealing with it as a steady state system. So we'll deal with that next time. Excellent. Good having you back. Good to see you again. Any questions, I guess, before we split up? Fantastic.